During a build, dependencies are fetched from repositories and are used by the Gradle build tool to produce your library or application. This is known as the supply chain for your project. Each of these parts of the supply chain can be a vector of attack which can lead to malicious code being executed or being bundled with your product. For example, an untrusted repository may be configured in your build which hosts unsafe dependencies. Or an attacker may manage to replace a hosted dependency jar file with a malicious version which would then be used by your project. Or the Gradle wrapper may be replaced by an attacker which would compromise your project. In this course, you will learn about features Gradle provides and best practices to secure each part of the supply chain. Projects can be configured to only use trusted repositories that are centrally managed. Content filtering can ensure that private internal libraries are queried only from internal repositories and not public ones. Dependencies can be queried for known vulnerabilities. Dependency checksums can be verified before they are used. The authenticity of a dependency can be verified using signature files. Even the Gradle wrapper and binary distribution can be validated. In this first chapter, we will learn how projects can be configured to only use trusted repositories that are centrally managed. Repositories can be specified in the repositories block of build files. In a project, there may be several subprojects, each with their own build file. For large projects, different subprojects may be owned by different teams. Each team will define the repositories in the build file of their subproject, and teams may wind up using different repositories. Here, the app subproject declares the Google Maven repository, and the client and server subprojects declare the Spring IO repository. A team may accidentally add an untrusted or insecure repository, where malicious libraries are hosted, which could then be included in the build. Gradle provides a way for repositories to be centrally declared and managed for all subprojects in the settings file. In the Gradle documentation, you can search for centralizing repository declarations. Here, you can see in the settings file, you can declare a dependency resolution management block in which you can declare repositories. The documentation also covers how to manage the behavior of repositories being declared both in build files and the settings file using the repositories mode. By default, the repositories declared in the build files override those declared in the settings file. If you want to be strict and not allow subprojects to declare repositories, you can use the fail on project repos mode, which will cause the build to fail if a subproject build file declares a repository. Let's see this in action. We'll copy the repositories from this build file. Then in the settings file, we can add the configuration block for dependency resolution management, in which we can paste the repositories. We can add the additional repository from the other build file, and we can also disable subprojects from declaring repositories in their build files by using the repositories mode set repositories mode fail on project repositories. Now, since the build files still declare repositories, the build will fail. So we can remove the repositories declared in the build files. Now if we run the build again, it should pass. The ownership of the settings file can be limited to people who know how to properly vet repositories before they are added. This way only trusted repositories are used and we don't have to worry about a team member accidentally adding a malicious repository to our build. If your organization has publicly accessible repositories that their projects use, it is likely that they will be secured and require authentication to connect to. In the repository configuration, you can provide credentials to authenticate to these secure repositories. In the documentation, you can go to supported protocols under declaring repositories in dependency management. There are a few ways of providing credentials for authentication. Let's go to the handling credentials section and look at the example here. As the documentation reminds us, never put credentials inside your build scripts or inside files that can be checked into version control. Instead, in addition to the URL of the repository, a name and credentials class can be provided. In this example, the repository name is MySecureRepository. Therefore, Gradle will look for two properties called MySecureRepository username and MySecureRepository password for the username and password. These properties can be defined through the usual Gradle property mechanisms. The Gradle properties file in the Gradle home folder, command line arguments, environment variables, or a combination of these. There are other credential classes supported too that will look at different properties. Alternatively, you can also configure authentication schemes. In this example, a credentials block is used to provide the username and password for basic authentication using environment variables. Let's go over how to do this in our sample project. We can declare a new repository that has the name company repo with the URL of https company.repo.com. And we will use the password credentials class. In our Gradle home Gradle.properties file, we can declare a property called company repo username. And we can set it to the developer team and company repo password. Gradle will use these for authentication to the repository. In this next chapter, we will learn how content filtering can ensure private internal libraries are queried only from internal repositories, not public ones. When you have a mix of public repositories such as Maven Central and a private company repository, you'd want private dependency artifacts to be queried only from the private repository. Let's add a math library as an implementation dependency. This artifact is only found in the company repository. When a project is built for the first time on a machine, Gradle doesn't know which repository would have the dependency artifacts, so it may query multiple repositories for them. If we take a look at the build scan, we can go to Performance and then Network Activity, where we can see all the network calls made to get dependency artifacts. We can see it queried multiple repositories looking for the math dependency artifacts: Spring.io, Maven Google, and Maven Central, in which it was not able to find them. It then queried the company repo, where it was found. It then downloaded the other math dependency artifacts from the company repo. From a security perspective, these calls being made to the public repositories could be viewed by a malicious agent who would then have gained knowledge on private packages at your company. They could then use this information in some type of attack. For this reason, you want to configure Gradle to query the private dependency artifacts only from the private repository. Gradle supports adding configuration that specifies certain libraries be fetched from a specific repository only. In the documentation, you can search for filtering and click on the filtering repository content link. Then you can click on the declaring content exclusively link where you can see in the repositories configuration, you can add an exclusive content block for a particular repository using a particular filter that will determine which libraries to exclusively fetch from this repository. In our sample project, we can add an exclusive content block for the company repository with a filter to include all com.gradle.training dependencies. So these will be exclusively fetched from this repository. I've cleared the local dependency cache so the math dependency artifacts along with its transitive dependency artifacts aren't locally available, so Gradle will have to download them again, and also so that Gradle doesn't remember which repository it last found them in. When I run a build, and we look at the build scan, we can go to Performance and Network Activity, and when we search for math, we can see only the company repository was queried for it. You can use Develocity build scans to inspect the dependency network activity and use repository content filtering to further secure your builds. Note that when Gradle searches for artifacts, it does so in the order in which the repositories are declared. You can move the company repository to the top of the list. However, there still may be times when queries for private dependencies are made to the other repositories. For example, if a project is using an old version of a private library that is deleted from the company repository, then when it is not found in the company repository, the other repositories will be queried. Using repository content filtering ensures that private dependencies are queried only against the private repositories. In this chapter, we will go over how to ensure dependencies being used have no known vulnerabilities that could lead to exploits to your project. Libraries can have known vulnerabilities in certain versions, which can be viewed in Maven Central when deciding which library or version to use as a dependency. Vulnerabilities in transitive dependencies are also listed. Using dependencies that have known vulnerabilities can lead to exploits, so this information is important to be aware of. You want to avoid using versions of a dependency with known vulnerabilities. However, you may pick a version of a dependency that had no vulnerabilities at the time, and sometime later, a vulnerability on the library or a transitive dependency could have been found. You want to be alerted if this happens and take action such as changing the version of the dependency. We will go over 3 ways that you can use to be alerted to known dependency vulnerabilities to ensure your builds remain secure. The first is to configure your IDE to inform you of known vulnerabilities. We will demonstrate how to do this with IntelliJ. The second is to use a Gradle plugin such as the Dependency Check plugin that provides a task that can run as part of the build and fail the build if vulnerabilities are found. The third is to use the GitHub dependency submission action for Gradle that allows you to see vulnerabilities found on GitHub and can also fail builds if vulnerabilities are found. You can read the documentation for your editor to learn how to configure it to alert you on dependency vulnerabilities. IntelliJ uses the Packer Checker plugin, which is enabled by default. Let's see it in action. In this example project, we have a dependency on an old version of Guava that has a known vulnerability, and an old version of Jackson DataBind whose transitive dependency has a known vulnerability. IntelliJ will by default underline these with yellow to indicate there is an issue. You can hover over to see more information. You can also view the Vulnerable Dependencies report by going to Code, Analyze Code, and Vulnerable Dependencies. Here you can see all the vulnerabilities, and also browse the dependency tree to see the transitive dependency hierarchy. You can configure IntelliJ to show vulnerable dependencies in red instead of yellow by going to Settings, Editor, Inspections, Security, and then selecting vulnerable dependencies and changing it to error. If you were using version catalogs, this also works. Note that even though IntelliJ highlights these as errors, the build itself does not fail. To have the build fail, you can use the Dependency Check plugin. In the Gradle plugin portal, you can search for Dependency Check and click on the OWASAP result. You can copy the apply line and use it in your project. Let's refresh the configs to pick up the plugin. And we can look at the documentation to learn how to configure and use the plugin. We can open both the GitHub page and the documentation link. The plugin works by downloading the known dependency vulnerabilities list from the National Vulnerability Database known as NVD, which is hosted by NIST. The first time the vulnerability check runs, it downloads the initial list, which can take several minutes, 20 minutes or more. It is important to be aware of this. The API calls to NVD will be faster if you obtain an API key and configure the plugin to use that. You can click on the link provided to obtain an API key. The plugin can also fetch known vulnerabilities from the Sonatype OSS index. To do this, you have to provide the appropriate credentials, which you can obtain using the link provided. The GitHub documentation also mentions potential issues you can run into and how to resolve them. In the documentation page, it's mentioned the main task you can run is the dependency check analyze. If you click on the analyze task on the left menu, there will be documentation on how to configure the task and the plugin. You can use the dependency check configuration block, and to provide the NVD API key, you can configure the NVD block inside it. The other main configuration you want to provide is the fail build on CVSS. This will configure whether to fail the build if vulnerabilities are found. When the plugin task runs, it gathers all the vulnerabilities found and calculates a score depending on how serious the vulnerabilities found are. This is known as the CVSS score. The higher the number, the more severe the vulnerabilities. You can read about the CVSS on the NVD website. Medium vulnerabilities have a score of at least 4. So we can configure the plugin to fail the build if at least medium vulnerabilities are found. Let's configure the dependency check block. And provide a value for fail build on CVSS of 4. We can also configure the NVD API key, which we will get from an environment variable. It is recommended not to put the credentials in plain text inside the build files or files that will be checked into version control. Now when we run the task, we can see it fails the build due to the dependency vulnerabilities found. Having the build fail is a more sure method of ensuring the dependency vulnerabilities are addressed immediately. A reminder, the first time this task runs on a machine, it can take 20 minutes or more to download the vulnerabilities list. Since it can be expensive, it may make sense to enable this check only on a build machine and not on developer machines. Developers can configure their IDE to alert if vulnerabilities are found. The third option to identify dependency vulnerabilities is to use the GitHub dependency submission action for Gradle. In GitHub, you can configure a setting to run an action for Gradle to submit the dependencies list to GitHub, which will analyze and look for known vulnerabilities. To do this, we can go to Settings, Advanced Security, and make sure Automatic Dependency Submission is enabled. You can also enable Dependent Bot Alerts. Under Actions, you can see the dependency submission ran. After the action is completed, you can go to Insights and click on Dependency Graph. Here you can see the known vulnerabilities that were found. You can use this feature to be alerted when there are new vulnerabilities found. In this chapter, we will learn how dependencies can be verified using their checksums before they're used. A hacker manages to gain access to a repository and replaces the jar file of the UX widgets 1.0 with a malicious version. Projects depending on this library would now fetch this corrupted version, which would run malicious code when the library is used. If the project uses Gradle build tool, there is a feature to validate the authenticity of dependencies before they are used by the project that would help protect against this scenario. In this chapter, we will go over how to configure Gradle to perform this validation and describe how it works at a high level. Let's go over how this works. There are two ways the authenticity of a dependency can be verified. The first is using the checksum of the dependency. The second is using a signature file. We'll go over the checksum method first. To calculate the checksum of a file, a hash algorithm such as SHA-256 looks at the contents of the file and creates a fixed length string representation of it, known as the hash or checksum of the file. The hash algorithm will always create the same checksum for a file if the contents have not changed. If the file has been altered or replaced, the algorithm will generate a different checksum. If the expected checksum of a dependency jar file is known, then we can store this expected checksum in a Gradle configuration file called verificationmetadata.xml. When the jar file is being downloaded onto a machine, Gradle can compute the checksum of the file and compare it against the expected value. If the values match, then Gradle will trust the jar file and use it for the build. If the dependency jar file has been altered or replaced, when the file is downloaded, the computed checksum will not match the expected value, and Gradle will fail the build with an appropriate error message. Before going over how to create the verification metadata file, let's go over a project where the verification metadata already exists. In this project, we have the Apache PDF Box library version 3.0.6 as an implementation dependency, as well as other dependencies for the tests. When we run the dependencies task, we can see Apache PDF Box has transitive dependencies, and so does JUnit. The verification metadata file is found under the Gradle directory called verification-metadata.xml. Let's go over the contents of this file. If we scroll to the components section, we can see an entry for every dependency, both direct, such as Apache PDF Box, and transitive, such as Fontbox and Commons Parent. We can also see entries for the test dependencies, as well as for plugins, such as Fuji Resolver, which is a plugin that's applied in the settings file. Plugins are dependencies that are downloaded, so they too need to be verified. If we look at the entry for the Apache PDF box library, we can see it has two artifacts, one for the jar and one for the POM file. Both files are downloaded, so Gradle will verify both of them. If you want only the jar files verified and not metadata files like POM files, you can go to the top of the file. Under Configuration, you can set Verify Metadata to be false. If this is false, only jar files will be verified. For each artifact, there is an expected checksum, and the algorithm used for the checksum can be seen here. In this case, it's SHA-512. There is an origin message for each checksum with the value verified. This indicates that the checksum has been manually verified by someone when this entry was added to the file. It's important to note these checksum values have to be manually verified. I will explain this more when I go over how to create this file. To summarize, there are two main sections in this file. The configuration at the very top, where we can tell it whether to only verify the jar files or not, and the component section, in which there's an entry for each dependency artifact, for which there's an expected checksum for the specified algorithm that has been manually verified by someone. Now let's go over how to create this file. In the documentation, you can search for verifying dependencies, and here you can search for bootstrapping, where you can see the command you can use to generate the verification metadata file. I will use Gradle W, so I'll copy the part after the Gradle binary. Upon inspecting this command, it may seem odd that the help task is being run. The main thing to focus on is the part before that. In the example project, I'll delete the verification metadata XML file and run the command to generate a new one. This command tells Gradle to write the verification metadata file and what algorithm to use for verifying the checksums. I want to use SHA-512 instead of SHA-256, so I'll change that. We can see it created the verification metadata.xml file. At the top, we can see the configuration section, and below that, the components. You can see it bootstrapped a checksum for each artifact. Scrolling to the right, the origin message is different. It says generated by Gradle instead of verified. This message tells us that Gradle generated what it thinks is the expected checksum. However, we need to manually verify it. When creating an artifact entry in the verification metadata file, Gradle looks at the dependency artifact that was downloaded, calculates its checksum using the specified algorithm, and bootstraps the expected checksum for that artifact in the file to be this calculated checksum. However, if the artifact was already compromised, then the calculated checksum cannot be trusted. The bootstrapped checksum needs to be manually verified. Let's go over how the checksum can be manually verified. Here is the library page for Apache PDF Box on mavenrepository.com. Files containing the expected checksum are published alongside the artifact file. For version 3.0.6, we can view all the files, and for each artifact, like the jar file, there are checksum files. If there were multiple algorithms used to generate the checksum, there would be a separate file for each one. Here, there is a file containing the checksum generated using the SHA-1 algorithm for the jar file, and a file containing the checksum generated using the MD5 algorithm. If there was a file for SHA-512, we could consult the value here. However, if the jar file was altered or replaced here, then chances are the checksum files would be too. So in addition to checking the checksum here if it was available, we also want to get it from a different location, not only from the repository. If we go back to the main page for the library, there is a link to the project page. Here we can click on Download, where we can see all the artifact files available to download, including the jar file. Checksums can be available here too. In this case, the SHA-512 checksum is available. We can copy this to compare it against the checksum generated by Gradle. Note that if the checksum we want wasn't available over here, we can download the artifact, in this case the jar file, from this alternate location and manually generate the checksum and use that for the comparison. We can search for the checksum we copied, and it should match the checksum generated by Gradle. With this, we have verified the checksum using an additional source. Depending on your security policies, you may want to verify it with additional sources even. This manual verification process can be time-consuming and tedious. However, it helps ensure the correct checksums are used. We can change the origin message to verified. Note that you can use a different string here instead of verified if your team prefers another convention. The verified string is what the Gradle team uses. In the Gradle GitHub project, you can look at the verification metadata file and search for the string verified. You can see there's a comment about changing the origin string to verified once the checksum has been checked. And in the file we can see places where origin has been changed to verified. If the checksum from the other sources does not match the one generated by Gradle, then this needs to be investigated. Sometimes there can be other reasons why the checksum is different, not necessarily due to a hacker. For example, the owner of the library may have accidentally published different files to the Maven repository versus the website. Either way, the discrepancy needs to be investigated. In the documentation, you can click on Dealing with the Verification Failure and reference the Incorrect Checksums section for guidance on how to proceed. Once all the checksums have been verified, you can add and commit the verification metadata file to the repository so others will be able to use it too. Every time a build runs, the dependencies will be verified using the checksums. If you add another dependency, here I will add the Jackson core library as an implementation dependency. If we run the build, it will fail since the expected checksums for the artifact of this new dependency and its new transitive dependencies are missing in the verification metadata file. We can rerun the task to write the verification metadata, and now there'll be entries for Jackson core and its transitive dependencies. And we can go through the process of manually verifying the checksums. Once the entries have been verified, if I run the build again, it passes. If there's a verification failure during a build, let me simulate this by changing a checksum. You will see an error message as follows: one artifact failed verification and the name of the artifact. Again, you can reference the documentation on how to proceed with the investigation. Verifying the checksums of dependency artifacts helps ensure your builds are secure. Now let's go over how we can configure Gradle to authenticate dependencies using signature files. Signature files allow more thorough confirmation of the owner of the dependency artifact. Signature files rely on public-private key pairs. A publisher of artifacts will have a pair of keys that work together, one public, the other private. They keep the private key to themselves. It is not shared with anyone. They publish the public key in key server repositories with a unique ID so anyone can get and use them. When the publisher wants to publish an artifact, they can create a special file called a signature file. The contents of this file can be used to verify the artifact. So to ensure its authenticity, the contents are signed using the publisher's private key. When this signature file is published to a repository and a user or tool downloads it, they can fetch the publisher's public key if they know the ID and use that to verify the signature. Only the corresponding public key from the public-private key pair can be used to verify the signature. If a hacker wants to replace the file, they would not have access to the publisher's private key, so they would have to use another private key to sign the new file and then upload this file to the repository. Then, when this file is downloaded and the publisher's public key is used to verify the signature, that will fail. Even if the original signed file is tampered with, the signature verification will fail. Once a publisher uses their private key to sign a file, it can only be verified using the publisher's public key and also only if the file is unaltered. Let's explore how this would work in verifying the authenticity of a dependency. When publishing an artifact, say the UX widgets 1.0 jar file, the publisher creates a separate file containing information about the artifact that can be used to verify it. The data in this file is created using the checksum, creation timestamp, and other metadata about the artifact. Then, this file is signed using the publisher's private key. It is then published along with the artifact. This separate file is known as a signature file and typically is named after the artifact file plus an additional .asc extension. The verification metadata configuration can be updated to include the correct ID of the public key associated with the dependency artifact. Then, when Gradle looks at the dependency artifact, in addition to verifying the checksum if it has been configured in the verification metadata file, it looks at the signature file as well. It will fetch the public key from the key server using the ID if it doesn't already have it cached, and then use the public key to verify the signature file. Once verified, it will compare the information in the signature file to the dependency artifact file. If the information matches, Gradle will trust the artifact. If the signature was not verified, or the information in the signature file doesn't match that of the artifact, the build will fail with an appropriate error message. Before going over how to run the command to update the verification metadata file to include signature file verification, let's go over what an already updated file looks like. This is the same project from before, which has Apache PDF box as an implementation dependency. If we look at the verification metadata file, we can see that for some artifacts, in addition to the expected checksum, there is a public key ID in the PGP XML element. Not all the artifacts have the public key ID. There could be a couple of reasons for this. First, if there was no signature ASC file for an artifact, it would not have a public key ID entry. Second, sometimes the public key would be for an entire group of artifacts. And in that case, the public key ID would be at the top of the file under the configuration section. Here, all signature files for the artifacts under the org.apache.pdf box group can be verified with this public key. And here, all signature files for the artifacts for the org.junit group can be verified with this public key. If there were keys that could not be found on the default public key servers, they would be added to the ignored keys section. I will cover what to do for these later in the chapter. You will notice that the verify signatures has been set to true. That means Gradle will check the signature file if there is one for the artifact. There are two additional files in the Gradle directory. These files contain the full public keys that were downloaded using the public key ID verification in the metadata file. That way, Gradle does not have to re-download them every time. If we look at the keys file, you can see it contains the full public key, including the owner information. The value for pub is the shortened version of the public key ID. I'll copy this one, and if we search for it in the verification metadata file, you'll see the full public key ID. Let's go over how to update the verification metadata file that only has the expected checksums to also have the public key IDs and perform signature verification. In the Verifying Dependencies documentation page, you can search for other occurrences of the word bootstrapping and find the next subtitle for it. There's a subsection on bootstrapping for signature verification. Here, the documentation points out that it is recommended to have both the checksum and signature verification enabled. Keep in mind that not all artifacts will have a signature file, so in those cases, at least checksum verification will be done. The documentation shows the right verification metadata command we need to run to generate configuration for both the checksum by specifying the algorithm to use, and signature verification. Running this command on an already existing configuration will add to the configuration, so if there are already checksum entries, the public key IDs will be added if there is a signature ASC file for the artifact. Therefore, it is safe to run this when there is already an existing configuration that has only the checksum entries. Here, the help task isn't run as shown in the earlier example. However, for consistency, I will run this command with the help task. To have the public key files also generated, if we scroll up slightly, we can see the export keys flag can be run. This flag can be added to the right verification metadata command as shown here. I'll copy this command. Here we have the sample project where now the verification metadata configuration only has the checksum entries. I'll paste the command copied from the docs. I'll change the checksum algorithm to SHA-512, and I'll run this with the help task. We can see the file was updated to include public key IDs for the artifacts. Some entries were added for groups of artifacts, and some for individual artifacts. Gradle used these public key IDs to download the full public keys from the default public key servers and stored the full public keys in the additional files. How did Gradle populate the public key IDs for the artifacts or groups? Where did it get these from? If we look at all the files that were published in the repository for Apache PDF Box 3.0.6, we can see that for the jar file, in addition to the expected checksum files, there is a signature ASC file that is also downloaded by Gradle. The same is true for the JUnit dependency. If we view all the files, we can see the jar file and the ASC file. If we open an ASC file, we can see it's not human readable. Gradle downloads the ASC file in addition to the jar file. Let's see how we can inspect the downloaded ASC file. Gradle downloads dependencies to the Gradle home folder under the caches directory. We can see the ASC file for the Apache PDF Box 3.0.6 as follows. And for JUnit 5.12.1 as follows. We can use the tool GPG to inspect the packets in the ASC files. Let's inspect the JUnit file first. we can see the public key ID. So Gradle gets the public key ID from the ASC file itself and bootstraps this value in the verification metadata file. Just like with the checksum, we need to manually verify that this is correct. That is, we need to manually verify that this is the correct public key ID for the publisher using a different source like the project website. If a hacker replaced the jar file, they could have replaced the ASC file too, and we cannot blindly trust the public key downloaded from the ASC file. We can go to the JUnit project page, and here we can go to the GitHub repository and look at the keys file, where the public key ID is listed. We can copy it and compare it to the one in the verification metadata file. It matches, so we have verified that this is the correct public key ID. Now let's verify the Apache PDF box public key ID. We can use the gpg command again to inspect the packets in the ASC file. Gpg list packets and the location of the ASC file. We can see the public key ID in the ASC file and copy it. And see this is the one bootstrapped in the metadata file. Now let's manually verify this is correct. We can go to the project page, and here we can click on the download link and look at the keys file. If we go to the bottom, here only the shortened ID is available. I'll copy it, and if we search for it in the metadata file, we can see it matches. Note that the keys file is also available on the project GitHub repo. So we could have verified the public key ID from here as well. I wanted to show both these examples to show that verifying the public key IDs can be different depending on what keys file the publisher uses. Sometimes there will be short public key IDs available, and the location of the keys file can differ. Manual verification can be time-consuming and tedious. However, it is crucial for security. After you have manually verified all the public keys are correct, you can commit the updates to the verification metadata file into version control, and Gradle will verify the signature files using the public keys configured if the ASC file for the artifact is present. Sometimes public key IDs in ASC files are not found in the default public key servers. When that happens, Gradle will put them in the ignored keys section. You can read the project page or contact the publisher to find out which key server their public key is available in, and then manually add it to the metadata file and the keyring file. The documentation has instructions on how to do this. After enabling both checksum and signature file verification, the integrity and authenticity of your dependencies can be verified and your builds will be a lot more secure. In this chapter, we will learn how to validate the Gradle wrapper and binary distribution that are being used for your builds. On January 11th, 2023, the Gradle team was contacted by maintainers of the Minecraft Online community regarding a security breach to their supply chain. A new contributor to the project had submitted a change request which got approved and merged. This change request included patched Gradle wrapper jars containing malicious code. When developers pulled in the change onto their local machines, the compromised wrapper jars were also pulled. When they ran the wrapper, it executed the corresponding compromised jar file, which ran the malicious code on their machines. Supply chain attacks include attempts to compromise the build tool. When you run the Gradle wrapper, it calls the Gradle wrapper jar, which looks at the Gradle wrapper properties file to determine the Gradle distribution to use. The Gradle wrapper then invokes that Gradle distribution. To protect Gradle against supply chain attacks means ensuring the integrity of both the wrapper jar and the Gradle distribution. In the documentation, you can search for wrapper integrity and click on the relevant result. Here, you can read how to validate the wrapper jar checksum to verify its integrity. For each Gradle release, checksums of the wrapper jar are also published. The documentation includes instructions for manually verifying the integrity by computing the jar file's checksum and comparing it against the official checksum. The instructions are available for different platforms. However, you want to automate and perform this check as part of the build process instead of manually verifying it. You can create a script with the steps and run that as part of your build process. Or, if you're using GitHub, there's a GitHub action that you can add that will perform this check. You can create the action that will run on every push and pull request, and it will validate the wrapper jar. I'll demo how to do this. Let's copy the workflow contents. You can either add the workflow in an editor and create a pull request, or add it directly through the GitHub project page. I'll do the latter. In Actions, I'll click on New Workflow, then set up a workflow yourself, and here paste the workflow contents. I'll call the workflow Gradle Wrapper Validation. You can create a pull request for your team to review. For this demo, I'll commit the action directly to the main branch. The action will run, and soon it will pass. Now, let's change the jar file to something different and see what happens. I'll create a new branch for the pull request and put a bad wrapper jar file. I'll commit and push my change. I'll create the pull request and the action will run for this pull request. And it will fail. This will alert the team that a pull request tried to introduce a non-official wrapper jar that could be malicious. Now that we know how to verify the integrity of the wrapper jar, let's turn our attention to the next link in the chain, the Gradle distribution itself. In the Gradle wrapper properties file, you can see the Gradle version the project will be built with. You can use the wrapper task to update to a new version of Gradle that may not exist on the machine yet. Here I will change the version from 9.3.0 to 9.3.1, which isn't on this machine. When I run any task, the wrapper jar notices Gradle 9.3.1 isn't on the machine, downloads it, and then invokes it with the task. You can verify the integrity of the Gradle distribution it downloads by also validating its checksum. The Gradle releases page also contains the checksums of the Gradle distributions. In the documentation, you can find information on how to validate the distribution using this checksum. In the Gradle wrapper properties file, you can add the distribution SHA-256 sum property. Then, when the wrapper downloads the distribution, it will compute the checksum and compare it against this value. Let's copy the property name. And I'll paste the property name here. And put the expected checksum. If you update the version of the Gradle distribution, you can update this SHA as well. Then, when the wrapper jar downloads the distribution, it will validate the integrity of the distribution. You now know how to verify the integrity of both the wrapper jar and the Gradle distribution. This is important to protect against supply chain attacks directed at the build tool. In this training, you have learned how to use Gradle features to secure your builds. There are additional measures you can take to secure your builds even further by using the features offered by Develocity. Next, we will learn a little about this.
Hello everyone. I'm going to talk about a critical but often overlooked area of the software supply chain, software provenance. Let's start with the why. In modern security, we spend a lot of time scanning finished artifacts for vulnerabilities. But there's a massive blind spot, the build process itself. If an attacker compromises your CI runner, a developer's local environment, or a trusted dependency to execute code or modify your build output, they can sabotage your software before it's even packaged. Software provenance is about answering this question. Where did it come from, and can you prove it? Without provenance, an artifact is just an anonymous file. With it, it's a verified product of a known, untampered process. We are moving beyond just scanning code to verifying the integrity of every input and tool that went into creating the final binary. Now, let's look at the solution. How do we actually achieve this level of verification at scale without slowing down our development teams? This is where Develocity Provenance Governor comes in. Provenance Governor is a continuous governance platform that uses the deep data already collected by build scans to create signed attestations. These attestations are signed facts. They go beyond a simple build log by providing a verified statement about the build context. Provenance Governor is a standards-based solution following the in toto specification for attestations. If you've worked with JWTs, the format here will feel similar. A payload of data containing facts about a subject is wrapped in a signed envelope. While in toto attestations use the DSSE standard rather than a JWT, the principle is the same. It's a tamper-proof package. Usually, the cryptographic hash of your binary, which permanently binds these verified facts to that specific build output. This ensures the provenance travels with the artifact and cannot be swapped or tampered with. So how does this actually work? It starts with Develocity build scans. You're likely already using these for observability, to see why a test failed or to troubleshoot a slow build. But in a security context, that deep observability is our superpower. The build scan acts as an immutable record of exactly what happened during the build execution, providing the transparent data layer you need to verify the build's integrity. Once the build completes, we run a post-build step where Provenance Governor takes the data from a build scan and generates the in toto attestations. One of the biggest wins here for security is that Provenance Governor handles all of the signing for you. Your CI runners don't need to store or manage sensitive private keys. Develocity Provenance Governor manages all of that complex work centrally. Finally, we store the evidence. Provenance Governor can push these signed facts to JFrog App Trust or an S3 bucket, ensuring your provenance data is safe and ready for audit. This allows us to run meaningful policy checks before moving to the next step of your pipeline or deployment. For example, we can verify, was this built using an approved JDK? Or were all the dependencies resolved from an internal hardened repository? If this evidence doesn't match your organization's standards, the policy fails, giving you the data you need to govern your software supply chain. Okay, let's look at an example. This project is already publishing build scans to Develocity, and I've updated the build to add a GitHub action to trigger the attestation publishing by the Develocity Provenance Governor. When this build finishes, we see the summary, but I can also dig into this and look at it inside of JFrog too. These attestations are attached to a Docker image. If I go to the Evidence tab, I can see each one of these attestations. We have evidence for which JDK was used, both a markdown format and the JSON that's inside of the DSSE. We have which build tool was used, which repositories were used in the build, the dependencies themselves, so a flat list of dependencies, very much like an SBOM, and a SALSA verification summary. I have another project that makes use of these attestations and evaluates policy against them. We can see in the summary that this policy has failed, and we can see why. An unapproved JDK was used. Your company may want to standardize on the JVM version or vendor. Maybe you want to avoid license fees, or maybe you are paying for support, so you want to make sure you're using the right one. This build also uses repositories that are not on an approved list. All the repositories here are well trusted. However, in a corporate environment, you should be routing all of your repository traffic through an internal repository manager. Maven Central, for example, is rate limiting, so that may slow down or break your builds. Depending on how your build is configured, you could also be leaking information to these remote repositories about your internal artifact names. And of course, you want to make sure untrustworthy repositories are never added to your build in the first place, as this may poison any dependencies. To wrap up, securing a build process is about more than just scanning your source code. It's about proving the integrity of the process that created your artifact. By using Develocity Provenance Governor, we move from a world of unverified binaries to a world of verified software. You get deep observability through build scans, cryptographically signed facts, a verifiable chain of custody, and automated governance.